A spacecraft billions of miles from home began slowing down against all predictions. This is the story of the pioneer Anomaly, a decades-long puzzle that challenged our understanding of physics itself. You will learn the complete detective story, from the first strange signal to the surprising culprit finally uncovered. We will explore how a tiny, unexplained force on two lonely probes sparked a search that ranged from simple heat leaks to the shadowy realms of dark matter. What does it take to solve a mystery when the evidence is drifting in the interstellar void? Their story begins not with a mystery, but with a bold declaration of human curiosity. In the early 1970s, two identical spacecraft named Pioneer 10 and Pioneer 11 were launched on trajectories that would make them true explorers of the unknown. Their mission was to go where no human-made object had gone before, acting as our robotic ambassadors to the outer solar system. Pioneer 10 had a singular, historic goal. It was the first spacecraft ever sent on a path to cross the treacherous asteroid belt, a region many feared would shred it to pieces, and then to conduct a close flyby of the giant planet Jupiter. Its success was a monumental relief and a triumph, beaming back the first ever close-up images of that swirling, storm-racked world. But Pioneer 11 was given an even more audacious task. After also visiting Jupiter, it used that planet's immense gravity like a slingshot, hurling itself on a new course toward the ringed jewel Saturn. This made it the first probe to ever visit both gas giants, a feat that paved the way for the more famous Voyager missions that followed. These pioneers were pathfinders in the truest sense, carving a trail through the cosmic dark. To understand the anomaly that later haunted them, you have to picture how they moved. These were not like the complex, thruster-packed probes we send today. They were elegantly simple, spin-stabilized craft. Imagine a dinner plate spinning on its edge on a tabletop. That spin keeps it stable, pointing steadily in one direction. The pioneers were like that, rotating several times per minute to maintain their orientation. They had no powerful, constant engines. Once they were flung away from Earth by their rockets, they were essentially coasting. They were bullets fired into the cosmic ocean, sailing on nothing but their initial momentum and the gentle, predictable tug of the sun's gravity. Every single force acting on them, from the faint pressure of sunlight to the pull of distant planets, was supposed to be meticulously calculable. Their trajectory was meant to be a perfect cosmic ledger, a testament to the clockwork precision of Newtonian physics. It was this very purity of their motion that would later turn their quiet journey into the perfect laboratory for detecting something terribly, wonderfully wrong. For years, the twin pioneers sailed on in radio silence, their missions officially complete. Yet scientists, a curious and stubborn breed, kept listening. They continued to ping the spacecraft with powerful radio signals from the global array of giant dishes known as the Deep Space Network. Every day, these meticulous calls and responses were logged, creating a decades-long record of each probe's position. The method behind this tracking is a beautiful piece of applied physics called the Doppler shift. You experience a version of it when a siren changes pitch as an ambulance speeds past you. The sound waves compress as it approaches, raising the pitch, and stretch as it moves away, lowering it. The Deep Space Network used this same principle but with radio waves. By measuring the precise frequency of the signal returned from a pioneer, engineers could calculate its velocity toward or away from Earth with astonishing accuracy, down to millimeters per second. This data was the ultimate fingerprint of the spacecraft's motion, a heartbeat monitor on a patient billions of miles away. And slowly, imperceptibly at first, that heartbeat began to show a faint, irregular flutter. When the team at NASA Jet Propulsion Laboratory processed the tracking data, they found something that made no sense. According to all their models, which accounted for the gravity of the Sun and every known planet, the pioneers should have been at a specific point in space. But the radio signals told a different story. The probes were ever so slightly closer to Earth than they should have been. The only way that could happen was if they were traveling just a tiny bit slower than predicted. An unseen force was applying a gentle, continuous brake. This discrepancy was almost laughably small, equivalent to a 10/1000th of the gravity you feel standing on Earth's surface. But in the pristine, frictionless environment of deep space, where every force is accounted for, it was a glaring anomaly. It was the first whisper of trouble, a single thread pulled from the tapestry of celestial mechanics. Someone or something had left a fingerprint on the pioneers. That whisper soon hardened into a number, a precise and stubborn figure that refused to go away. After years of data, the anomaly was quantified as a tiny, unrelenting acceleration back toward the Sun, measured at approximately 8.74 times 10 to the minus 10 meters per second squared. To grasp just how small this force was, imagine the gentle gravitational pull you would feel from a single coin, a dime or a penny, if it were placed over 8,000 miles away from you. It is an almost imperceptible tug, utterly drowned out in the noise of daily life on Earth. But in the silent, near-perfect vacuum of interstellar space, where every other force had been meticulously subtracted from the equations, this faint whisper became a shout. It was the equivalent of the spacecraft slowing by about 1 inch per second every single second. Over a decade, that adds up to thousands of miles of deviation from their predicted path. More intriguing than its size was its behavior. This anomalous push back toward the Sun was constant. It did not fade or fluctuate, and crucially, it was affecting both Pioneer 10 and Pioneer 11 in exactly the same way, even though they were billions of miles apart on different trajectories. This fact was a critical clue. It immediately ruled out a simple, one-time engineering mishap, like a stuck thruster or a piece of debris hitting one probe. A random event would not create such a perfect mirrored effect on two separate vehicles. The consistency pointed away from a mechanical fault and toward something far more profound, a potential new physical phenomenon, a subtle rule of the cosmos that our textbooks had somehow missed. The universe itself seemed to be applying a gentle, universal brake, and two silent ambassadors were sending back the evidence. Faced with this persistent cosmic whisper, the investigation had to begin with the mundane before leaping to the miraculous. The detectives on Earth first turned their scrutiny inward toward the spacecraft themselves. Could a simple engineering flaw explain the anomaly? The most obvious suspect was a tiny, undetected gas leak. The Pioneers did carry small thrusters for occasional attitude control, and even a minuscule, steady leak of propellant could, in theory, push against the direction of travel. Yet the evidence was against it. These thrusters were used sparingly, and telemetry showed no signs of the pressure drops or unexpected firings that would accompany such a leak. More importantly, the thrusters were pointed in specific directions. A leak would have nudged the spacecraft in ways that would have shown up as rotational wobbles, not a clean, straight-line deceleration. This suspect, while logical, had a solid alibi. Attention then turned outward to the environment of space itself. What known forces were acting on the probes? One candidate was the gentle pressure of sunlight. Photons from the Sun, though massless, carry momentum, and they constantly push against any surface they strike. This solar radiation pressure is a real force, carefully accounted for in mission planning, but its signature was wrong. The push from sunlight weakens dramatically as a spacecraft moves away from the Sun, following the inverse square law. The Pioneer anomaly, however, remained stubbornly constant as the probes ventured into the far outer solar system. The numbers simply did not match. The Sun's push was fading into insignificance just as the anomalous tug held firm. Could there be unseen masses tugging at the probes? Some scientists wondered about the gravitational influence of the Kuiper belt, that distant disk of icy debris beyond Neptune. Perhaps its collective gravity was providing an extra pull. but calculations showed its total mass was far too small to produce an effect of this magnitude. Furthermore, if the Kuiper belt were massive enough to slow the Pioneers, its gravity would also have visibly perturbed the orbits of Uranus and Neptune in ways that astronomers had never observed. This suspect too was eliminated for lack of motive and means. Finally, what about simple drag? Even the near-perfect vacuum of interstellar space contains a sparse mist of dust and gas. Could the Pioneers be plowing through this thin medium, experiencing a tiny but constant form of aerodynamic drag? Again, the physics said no. For drag to produce a constant acceleration, the density of the interstellar medium would have to be thousands of times greater than all our best measurements indicated. It was like suggesting a car coasting on a highway was being slowed by a fog so thick you could not see it, while every instrument reported clear skies. Each conventional explanation, when held up to the cold light of data, crumbled. The usual suspects had been rounded up and questioned, and everyone had an airtight alibi. This left the investigation team with a chilling and exhilarating realization. The culprit was not a faulty valve or a dusty corner of the solar system. It might be something entirely new, a faint signal from the hidden rulebook of the universe itself. The most promising suspect was not outside the spacecraft, but within its very heart. Every machine gives off waste heat, and the Pioneers were no exception. Their primary power source was a set of radioisotope thermoelectric generators, or RTGs. These remarkable devices had no moving parts. Instead, they converted the steady, decaying heat from pellets of radioactive plutonium directly into electricity to run the spacecraft's instruments and transmitters. But this process was not perfectly efficient. A significant portion of that nuclear heat was simply waste, radiating away into space as infrared light. This fact alone was not suspicious. Heat radiation is a known force. Every photon of infrared light carries a tiny amount of momentum away from the spacecraft. In a perfectly balanced system, if heat radiated equally in all directions, these tiny pushes would cancel each other out, resulting in no net force. But the Pioneers were not perfectly symmetrical objects. Their design created a potential bias, a preferred direction for this radiation to escape. The key feature was their large, parabolic dish antenna, over 9 feet wide, which always pointed directly back at Earth for communication. Think of this dish not just as a receiver, but as a mirror. The RTGs and the warm electronics box were mounted on long booms extending from the sides of this central structure. Now picture the infrared glow from these warm components. Some of that heat radiation would shine directly out into space, but a portion of it would strike the back of that large, curved antenna dish. And just like a curved mirror can focus light, this parabolic dish could reflect and focus that waste heat. Crucially, the dish was pointed at Earth, which meant its concave surface was facing forward along the spacecraft's direction of travel. If the dish reflected a significant amount of the spacecraft's own heat radiation forward, then the photons would be shot out in that direction. According to Newton's third law, for every action there is an equal and opposite reaction. If you throw a rock backward, you move forward. If the Pioneer was, in effect, throwing trillions of infrared photons forward, the reaction would be a tiny push backward. From the perspective of Earth, tracking a spacecraft that was being pushed backward along its path, it would look exactly like a constant acceleration slowing it down, a gentle drag pulling it back toward the sun. This idea was termed anisotropic thermal radiation. Anisotropic simply means having properties that differ depending on direction. It was the hypothesis that the Pioneer's heat was not escaping evenly, but was being funneled, however slightly, in one specific direction by their own hardware, turning the spacecraft into an incredibly faint, unintended photon rocket. It was an elegant and compelling explanation born entirely from the probe's own engineering. It required no new physics, no dark matter, no revision of gravity. It simply required a careful, painstaking audit of every warm surface on a pair of machines billions of miles away. The hypothesis was elegant, but proving it was a monumental task. To know if heat was the culprit, scientists had to perform a virtual autopsy on the pioneers, recreating every square inch of their complex thermal anatomy inside a supercomputer. This was not a simple calculation of a light bulb's glow. The spacecraft were intricate machines, each component a patchwork of different materials with unique properties. Some surfaces were shiny metal, reflecting heat like a mirror. Others were blackened or coated in insulation, absorbing warmth and re-radiating it slowly. The heat from the RTGs did not travel in a straight line. It would bounce off the back of the antenna dish, warm a strut, which would then warm a nearby electronics box, creating a cascading web of thermal influence. To model this accurately, researchers had to account for every bolt, every wire, every layer of gold foil and black paint. They built digital twins of the probes, dividing their surfaces into thousands of tiny facets, each one calculating how much heat it received, absorbed, and emitted every second of the decades-long mission. It was a staggering computational puzzle, a forensic reconstruction of warmth in the absolute cold of space. Early results from these painstaking models were tantalizing, yet inconclusive. They showed that anisotropic thermal radiation was indeed a powerful force. The geometry of the spacecraft, with its large forward-facing antenna acting as a reflector, did funnel a significant amount of infrared photons in the direction of travel. The push from this photon exhaust was real, and it was substantial. According to some of the first comprehensive studies, this thermal recoil could explain a large portion of the anomaly, perhaps as much as 70 or 80% of that mysterious 8.74 figure. This was a major breakthrough. It meant the most exciting possibility, a revolution in physics, was likely receding. The universe's rulebook was probably safe. Yet a stubborn gap remained. Even the best early models could not account for the entire anomalous signal. There was still a tiny residual acceleration, a whisper within the whisper that the thermal models could not silence. This gap was both frustrating and electrifying. It kept the door to new physics ever so slightly ajar. Could it be that thermal effects explained almost everything, and the leftover was merely uncertainty in the impossibly complex model itself? Or was that leftover the true signal of something deeper, masked but not erased by the spacecraft's own warmth? For years, this ambiguity was the state of the mystery. The thermal hypothesis had risen as the prime suspect, but it could not be fully convicted. The case remained open, waiting for a final, definitive piece of evidence that could account for every last fraction of that anomalous drift. The detectives needed a better model, and more importantly, they needed to find the lost blueprint of the suspects themselves. The investigation now faced a deadline set not by funding or will, but by the cold, irreversible laws of physics. The pioneers themselves were dying. Their nuclear power sources, those steady hearts of plutonium, were decaying. Each year, they produced a little less heat, a little less electricity. The faint whispers from the void were growing fainter still. Mission controllers made the difficult decision to prioritize. To conserve power for the most critical systems, they began turning off instruments one by one. The once busy streams of scientific data dwindled to the bare essentials: the spacecraft's heartbeat, its temperature readings, and that precious, unbroken radio link used for tracking. Pioneer 11, the trailblazer to Saturn, fell silent first. Its last coherent signal was received in November 1995. Pioneer 10, the Jupiter Pathfinder, held on longer, sending back engineering data until a final, whisper-weak signal in January 2003. After that, there was only silence. The two witnesses to the anomaly could no longer speak. Their testimony was now entirely historical, locked in the data collected over 3 decades. This created a profound and very human challenge for the scientists racing to solve the puzzle. They were not just analyzing numbers, they were becoming digital archaeologists. The most critical evidence, the raw telemetry detailing every shudder and shiver of the spacecraft, was recorded on aging, obsolete media. Think of massive reel-to-reel tapes, the kind you might see in old movies about mission control. These tapes held the precise record of thruster firings, power levels, and component temperatures, the very clues needed to calibrate the thermal models. But technology had moved on. The machines that could read these specialized formats were museum pieces, if they existed at all. Some data had been transcribed to newer systems over the years, but the process was imperfect. Logbooks were misplaced, metadata was lost, and bits of the pioneer's life story were scattered across different archives and institutions. The fear was that the definitive answer might be trapped on a forgotten tape in a dusty basement, slowly degrading into magnetic silence. This race against entropy added a layer of poignant urgency to the work. Every scientist on the case knew they were not just solving an equation, they were recovering a legacy. They were piecing together the final, fading diary of two of humanity's greatest explorers before the details were lost forever. The pressure was immense. Could they reconstruct the thermal portrait of the pioneers with enough fidelity to close the case before the evidence itself evaporated? Or would the anomaly remain an eternal question mark, a ghost in the machine whose truth faded with its signal? The solution would require one final Herculean effort, a deep dive into the ghosts of data passed to build a model so complete it could silence the cosmic whisper for good. From the silence of the void, a new voice emerged to champion the mystery. In the early 2000s, a physicist named Slava Turyshev refused to let the pioneer anomaly fade into the footnotes of history. Convinced the answer lay buried in the data, not in new laws of physics, he spearheaded a monumental rescue operation. This was not a casual review, it was a full-scale forensic exhumation, a mission to recover every last digital whisper from the pioneers before they were lost forever. They called it the Pioneer Anomaly Revival Project, and its goal was audaciously simple: to build a thermal model of the spacecraft so precise, so complete, that it would account for every last fraction of that mysterious deceleration. To do that, they needed the raw evidence, the unedited diary of the probe's long journey. The challenge was staggering. The relevant data spanned over 30 years and was scattered across the country on obsolete media. Turyshev and his team became digital archaeologists, hunting down old 9-track tapes and crumbling mission logs from the archives of NASA, from the Jet Propulsion Laboratory, and from universities. Many of these tapes were not just old, they were recorded in proprietary, forgotten formats. The team had to track down and refurbish the original, bulky tape drives from the 1970s just to read them, often piecing together working systems from spare parts found in warehouses. It was a race against a slow, magnetic decay. Once read, the data was a chaotic puzzle. Telemetry streams from different eras used different calibrations, different recording intervals. A temperature reading from 1978 might be stored in a different unit or logged with a different identifier than the same reading from 1985. The team had to meticulously cross-reference everything, rebuilding a coherent timeline from millions of data points. This was not just tracking data, it was the internal biography of the machines, the ebb and flow of electrical power from the aging RTGs, the minute temperature readings from dozens of sensors on the antenna, the electronics box, and the instrument booms. Every spike and dip was a clue, a record of how heat flowed and pooled within the spacecraft's body over decades. This Herculean effort yielded a treasure that had never existed before, a unified, comprehensive dataset for both Pioneer 10 and Pioneer 11. For the first time, scientists could see the entire thermal life story of the probes, from their warm, active youth near Jupiter to their cold, quiet senescence in interstellar space. With this complete record in hand, the final and most sophisticated phase could begin. The team fed every recovered data point, every temperature reading and power level into an immensely detailed computer model. This was not a theoretical sketch, it was a dynamic simulation. The model could now calculate day by day over 30 years exactly how much heat each component generated, where that heat traveled, and most crucially, in which direction it was finally radiated into space as infrared light. It could account for the warmth from the instruments when they were powered on for a flyby, and the slow cool down when they were switched off years later. This was the definitive audit, the one that would finally balance the cosmic books. The stage was set for a verdict. Would the numbers finally align, proving the anomaly was a self-made phantom of escaping heat? Or would a stubborn discrepancy remain, a silent signal that something truly unknown was still at work in the dark? The verdict arrived not with a bang, but with the quiet certainty of a balanced equation. In 2012, after years of digital archaeology and computational modeling, Slava Turashev's team published their definitive analysis. Their work was the most comprehensive thermal portrait of the Pioneer spacecraft ever created, a simulation so detailed it could account for the warmth of every bolt and wire over 3 decades. This model did not rely on averages or estimates. It was fed by the actual recovered telemetry, the day-by-day heartbeat of the probes. It tracked the heat from the radioisotope thermoelectric generators, the warmth bleeding from the electronics boxes, and even a crucial, subtle detail often overlooked, the steady decay of their plutonium-238 fuel. This radioactive heart was not a constant. Its power output decreased predictably over time, meaning the amount of waste heat available to radiate also diminished year after year. A perfect model had to account for this slow fade. When they ran the final simulation, the numbers aligned with breathtaking precision. The model calculated the total anisotropic thermal radiation, the net photon thrust from all that carefully mapped heat escaping in a lopsided manner. It produced a predicted value for the anomalous acceleration. That prediction matched the observed 8.74 times 10 to the minus 10 meters per second squared almost exactly. The stubborn whisper from deep space had been perfectly reproduced in a supercomputer on Earth. The conclusion was inescapable. The entire Pioneer anomaly could be explained by the gentle, relentless push of its own waste heat. The primary force came from the radioisotope thermoelectric generators and their housing, but it was not a simple story of heat shining from the front. The complex geometry of the spacecraft was key. Heat radiated from the generators would bounce off the back of the large, forward-facing antenna dish. This reflection directed more infrared photons out into space along the direction of travel. According to Newton's third law, for every photon pushed forward, the spacecraft experienced a minute recoil backward. Over decades, this recoil summed up to the exact drift that had baffled physicists. The Pioneers had been their own faint, unintended photon rockets, slowing themselves down with the very energy that kept them alive. This was the potential solution to the decades-old mystery. The culprit was not dark matter, nor a flaw in Einstein's theory of gravity. It was engineering physics meticulously accounted for at last. The universe had not broken its own rules. Instead, human ingenuity had finally succeeded in modeling all the rules at play on a pair of distant, silent machines. The phantom acceleration had a material cause, one that was with the probes from the very beginning, baked into their design. It was a testament to both the limits of our initial understanding and the power of persistent investigation. The anomaly was not a signal from the unknown abyss, but an echo of the spacecraft's own warm heart, finally heard and understood. Yet for a mystery that had captivated the world for decades, the resolution felt almost too neat. Science thrives on healthy skepticism, and the 2012 thermal explanation did not silence every critic. A chorus of physicists raised pointed questions, arguing that the case might not be as definitively closed as it seemed. Their doubts centered on the immense complexity of the models themselves. To recreate the thermal environment of a spacecraft billions of miles away, researchers had to make assumptions. They assigned emissivity values to materials, estimated how much heat was reflected versus absorbed by each surface, and modeled the intricate shadowing effects of one component on another. Could tiny errors in these assumptions, critics asked, have conspired to produce a seemingly perfect match? Perhaps the model was not a precise reflection of reality, but a sophisticated piece of curve fitting, tuned to explain the anomaly after the fact. Furthermore, some analyses pointed to a tiny, stubborn residual. Even the most comprehensive thermal model might account for, say, 98% of the observed drift. But that remaining 2%, though minuscule, was mathematically significant in the pristine context of deep space. Was it simply noise, the inevitable uncertainty in measuring something so incredibly faint? Or was it a genuine signal, a whisper of something else that the thermal story could not explain? The debate grew more nuanced when comparing the two spacecraft. The thermal model for Pioneer 10 was considered exceptionally robust thanks to a richer set of recovered telemetry. Pioneer 11's data record, however, was less complete. Its journey was more complex, involving the gravity slingshot at Saturn that altered its attitude and thermal profile in ways harder to simulate. Could scientists be as confident in the explanation for Pioneer 11 as they were for its twin? This asymmetry left a sliver of doubt. The leading theory had overwhelming evidence, but absolute 100% certainty is a rare commodity at the frontiers of knowledge. This inherent ambiguity is what keeps the door to alternative ideas ever so slightly ajar. For some researchers, the allure of a more profound answer never faded. What if that residual push was not an error but a clue? It kept alive speculative, thrilling possibilities, perhaps a subtle interaction with the fabric of spacetime itself, or a hint of physics beyond our current models. In the end, the thermal explanation stands as the victor, the solution embraced by the majority of the scientific community. It is elegant, it requires no new physics, and it fits the data beautifully. But the story of the Pioneer anomaly teaches us that in science, a solved mystery often leaves behind a faint, fascinating echo of doubt. A reminder that our understanding is always a work in progress and that the universe guards its final secrets closely. While the thermal explanation slowly built its case, the mind naturally raced toward grander possibilities. Before the data could conclusively point to a warm spacecraft, it was far more thrilling to consider a cold cosmic mystery. If the anomaly was not a mundane engineering effect, then it had to be a message, a faint signal from the hidden 95% of the universe we do not understand. This line of thinking gave birth to two captivating, exotic hypotheses that turned the pioneers into unwitting probes of fundamental physics. The first proposition was as shadowy as it was elegant. What if the pioneers were not sailing through a perfect vacuum, but through an invisible fog? Scientists theorized that our solar system might be embedded in a diffuse, local halo of dark matter. This mysterious substance, which makes up about 85% of the matter in the cosmos, does not emit, absorb, or reflect light. It reveals itself only through its gravitational pull on galaxies and stars. Could there be a thin, undetected cloud of it right here in our own celestial neighborhood? If so, as the pioneers moved through this ghostly medium, its collective gravitational tug would act as a form of drag, a gentle brake applied by the unseen fabric of the cosmos itself. It was a beautiful idea. Two human-made objects by sheer accident were measuring the density of dark matter in our backyard. The math was even tentatively promising. To produce the observed deceleration, the required density of this dark matter halo would need to be only slightly higher than some models predicted. For a time, it seemed perfectly plausible. The pioneers' unexpected slowdown could have been our first direct measurement of dark matter's local effects, a historic discovery born from a navigational glitch. It framed the anomaly not as an error but as an accidental telescope pointed at the invisible universe. An even more radical idea challenged the foundations of physics itself. For centuries, we have relied on Newton's laws of motion and gravity, perfected by Einstein, to predict everything from a falling apple to the orbit of Pluto. These laws are spectacularly successful, but what if they are subtly incomplete? A theory known as modified Newtonian dynamics, or MUND, proposed exactly that. Its central premise is that gravity behaves differently at extremely low accelerations, the kind experienced in the outer reaches of galaxies, or by a spacecraft drifting in the deep quiet far from the Sun. In these regimes where gravitational forces become vanishingly faint, MUND suggested that Newton's familiar inverse square law needs a tiny adjustment. The mathematics of MUND showed something astonishing. When you applied its modified equations to an object on a trajectory like the Pioneer's, it predicted an anomalous acceleration almost exactly matching the observed value. It was not a fitted parameter or an added substance, it was an output of the theory. For proponents of MUND, the Pioneer anomaly was not a puzzle to be solved, but a prediction confirmed. It was potential evidence that our understanding of gravity itself was due for a revision, and that two lonely probes had just provided the crucial data point from the frontier. This was the ultimate what-if scenario, the possibility that the anomaly was not a problem with our spacecraft but a flaw in our cosmic rulebook revealed by humanity's farthest-flung machines. These exotic explanations, the dark matter drag and the rewrite of gravity, captured the public imagination for a reason. They transformed the story from a technical detective story into a cosmic revelation. They spoke to a deep hope that our forays into the void would uncover not just new places but new principles. For years, they represented the thrilling alternative to a simple heat leak, a reminder that sometimes the most exciting answer is not the one you engineer, but the one the universe engineers for you. They kept the mystery alive with the promise of a revolution. Ultimately, the Pioneer anomaly's greatest triumph was not in rewriting physics but in refining engineering. This decades-long cosmic detective story left a profound and practical legacy, one etched into the blueprints of every deep space mission that followed. The lesson was clear: in the silent expanse beyond the planets there are no small forces. Every photon of heat, every whisper of radiation must be accounted for with obsessive precision. This new standard is most visible in the design of missions like New Horizons, the piano-sized probe that gave us our first breathtaking close-ups of Pluto. From its inception, New Horizons was built with the ghost of the Pioneers looking over its shoulder. Its engineers knew their spacecraft would also rely on a radioisotope thermoelectric generator for power in the frigid outer solar system. But they refused to let it become a source of navigational mystery. The solution was elegantly simple in concept, yet critical in execution. Instead of mounting the RTG close to the main body of the spacecraft, they placed it on the end of a long boom, a mechanical arm that extended out to the side. This single design choice created a crucial thermal separation. The intense waste heat from the generator now had a clear, unimpeded path to radiate directly into space, rather than washing over the sensitive electronics and instruments or bouncing off the antenna. It minimized the chance for that heat to be redirected in a lopsided way that could push the spacecraft off course. Think of it like holding a hot coal at arm's length instead of clutching it to your chest. You manage the heat where it can do the least harm. But the lessons went beyond just placement. Modern mission planners now treat thermal radiation not as a passive byproduct, but as an active force to be managed. Spacecraft are meticulously modeled to ensure their heat radiates as symmetrically as possible, balancing the photon thrust from all sides. For missions requiring absolute trajectory precision, like those aiming to enter orbit around a distant world or to perform a delicate gravitational slingshot, engineers have another tool: small, controllable thrusters. These are not for major course changes, but for tiny, exquisitely fine adjustments. They can fire in minuscule pulses to counteract any residual, unmodeled forces, whether from a tiny thermal nudge or the faint pressure of sunlight. This is the ultimate synthesis of the Pioneer lesson. We may not be able to eliminate every microscopic force, but we can measure them and compensate for them with even greater intelligence. The Anomaly, therefore, did not hinder exploration, it advanced it. It forced a generation of engineers to think more deeply, to model more completely, and to build more wisely. What began as a frustrating whisper from two aging probes became a masterclass in deep space craftsmanship. The Pioneer's unintended legacy is a fleet of successors that fly truer, their paths more predictable, because we learned to listen to the quietest voices in the void. The true scale of this precision is almost beyond human comprehension. To plot a course across the solar system, you cannot simply draw a line from Earth to Jupiter. You must instead calculate a path through a dynamic, shifting web of gravity wells, where every single massive body exerts a continuous, changing pull. This discipline is called astrodynamics, and it is a ballet of mathematics performed in the void. The primary choreographer is the sun's immense gravity, but it is not the only dancer on the stage. Engineers must account for the gravitational tug of every planet, not just the one being visited. As a spacecraft approaches Jupiter, for instance, the calculations include the subtle, ever-present influences of Saturn, Uranus, and even the distant Neptune. They factor in the moon's pull when the craft is near Earth and the collective gravity of the asteroid belt when it passes through. These are known as perturbations, small deviations from a simple two-body orbit, and they are meticulously modeled. But gravity is only part of the story. A spacecraft sailing from the sun is also pushed by the light itself. Solar radiation pressure, the physical force of photons striking its surfaces, is a constant, gentle breeze. For a large, sun-facing surface like a solar panel or an antenna, this push is significant and must be included in the flight plan. Then there are forces so faint they seem like whispers. The spacecraft's own radio signal, beamed back to Earth, carries momentum. Transmitting that signal exerts a minuscule recoil on the vehicle, a force so small it was once laughable to consider. Yet in the pristine environment of deep space, where a drift of millimeters per second can compound into a miss of thousands of miles over a decade, nothing is laughable. The Pioneer Anomaly was the ultimate lesson in this reality. It screamed that our catalogue of known forces was incomplete, that something, whether thermal or fundamental, was acting on our probes and had not been added to the equation. It served as a masterclass in humility for the entire field. The Anomaly taught engineers and physicists that to truly navigate the solar system, we must move beyond the textbook simplifications. We must become accountants of the infinitesimal, tracking every conceivable source of momentum transfer, no matter how seemingly insignificant. It forced the realization that a spacecraft is not an abstract point mass following a perfect curve. It is a complex, warm, radiating object interacting with its environment in countless subtle ways. This relentless pursuit of precision is what allows a mission like the recent OSIRIS-REx to touch an asteroid billions of miles away and return a sample, or the James Webb Space Telescope to station itself perfectly at a gravitationally balanced point a million miles from Earth. Each of these triumphs rests on a foundation of calculations that now include lessons hard-won from two lonely pioneers. Their unexpected drift did more than solve a mystery. It raised the standard for every mission to come, proving that in the cosmic ocean, success depends on listening to the quietest of tides. Perhaps the greatest discovery from the Pioneer Anomaly was not about physics but about process. This quiet drama, stretching across half a century, stands as a perfect case study in the scientific method in its purest form. It began with a meticulous observation, a tiny, persistent discrepancy in the data that refused to be ignored. That observation sparked a cascade of hypotheses, from the mundane to the magnificent gas leaks, dark matter, modified gravity, and thermal radiation. Each idea was a possible thread to pull. What followed was a decades-long investigation, a global effort involving orbital mechanics, deep space archaeology, and supercomputer modeling. Finally came the revision. The preponderance of evidence pointed not to a new law of nature, but to a more complete understanding of an old one, forcing a refinement of our engineering models and our intellectual humility. This entire journey was science doing exactly what it is supposed to do, proving that the method itself is more reliable than any single theory. Our physical laws are not divine commandments etched in stone. They are incredibly powerful, beautifully precise models of reality, but they are models nonetheless. They are maps, and like any map, they are most accurate in the well-charted territories where they were drawn. The Pioneer spacecraft ventured into a new kind of frontier, not just of distance but of environmental purity. In the near-perfect vacuum of deep space, where the roar of Earth's atmosphere and the jostle of planetary gravity fade to nothing, the map's faintest imperfections can become visible. The Anomaly was one such imperfection. It was a reminder that every scientific rule we hold dear is provisional, constantly stress-tested at the edges of our experience. This is not a weakness, but the core strength of the scientific endeavor. It means our understanding is never finished, always open to correction by a stubborn piece of data from a silent probe a billion miles away. So, where does this leave the grand, revolutionary hope? The allure of discovering dark matter or rewriting gravity with this one mystery was undeniably thrilling. It promised a dramatic leap, a sudden rewriting of textbooks, yet the thermal explanation offers a different, perhaps more profound kind of victory. It demonstrates that our existing toolkit, Newton's laws, thermodynamics, and relentless computation, is capable of solving even the most esoteric puzzles, provided we apply it with enough care and honesty. The true value of the Pioneer Anomaly may ultimately lie not in the answer, but in the rigorous, self-correcting journey it demanded. It forced scientists to question their most basic assumption, that they had accounted for every force. It made them dig through forgotten archives and rebuild antique tape drives. It celebrated the painstaking, unglamorous work of checking your work again and again until the numbers finally align. In a culture often obsessed with dramatic breakthroughs, this story is a testament to the quiet power of simply getting the details right. It is a lesson in humility before the cosmos, acknowledging that sometimes the universe is not hiding a grand secret, but patiently waiting for us to notice a clue we left in the blueprint all along. But the Pioneer Anomaly was not the only navigational ghost haunting our spacecraft. Just as one mystery seemed to settle, another, even more peculiar one was being whispered about in mission control rooms, this time much closer to home. It became known as the flyby anomaly, and it defied explanation in a completely different way. This puzzle did not involve a constant, gentle drag in deep space, but a sudden, unexpected kick during the most delicate and precisely planned maneuvers in the solar system, gravity assist flybys of Earth itself. The principle of a gravity assist is a masterpiece of celestial mechanics. A spacecraft swings close to a planet, stealing a tiny fraction of that world's orbital momentum to slingshot itself onto a new path, saving immense amounts of fuel. Engineers calculate these trajectories down to the millimeter, knowing exactly how much speed the spacecraft should gain or lose. Yet, for several missions, the post-flyby tracking data revealed a tiny, inexplicable discrepancy. The probes were moving just a fraction faster than they should have been. The first notable case was the Galileo spacecraft bound for Jupiter during its Earth flyby in December 1990. As it whipped around our planet, it gained an extra 4 millimeters per second of speed, a minuscule amount, but one that was completely unaccounted for in the models. Then, in January 1998, the asteroid bound near Shoemaker spacecraft experienced an even larger anomaly during its flyby. gaining about 13 millimeters per second. Like a stone skipping across a pond and somehow leaping farther than physics allows, these spacecraft received an unexpected boost. The contrast with the Pioneer case is stark. The Pioneer anomaly was a slow, constant pressure, like a faint but persistent headwind in interstellar space, affecting two identical probes on similar long-term journeys. The flyby anomaly, however, was a brief, sporadic spike, a momentary ghost in the machine that appeared only during specific high-speed planetary encounters. It seemed tied to the geometry of the flyby itself, possibly influenced by the spacecraft's altitude, its incoming angle, or even which hemisphere it passed over. This made it far more frustrating to study. You could not gather decades of data. You had one brief, high-stakes event, and then the anomaly was gone, leaving only a confusing number in its wake. While the Pioneer mystery pointed toward a systemic force, either thermal or fundamental, the flyby anomaly felt like a glitch in the cosmic matrix, a fleeting reminder that our mastery of orbital mechanics might have a blind spot right in our own backyard. For years, scientists proposed a zoo of potential explanations, each more intriguing than the last. Some wondered if it was an effect of Earth's uneven gravity field, or the drag of a slightly extended atmosphere at high altitude. Others looked to more exotic ideas, like subtle interactions with the planet's magnetic field, or even minute errors in how we account for the tides raised on Earth by the Moon and Sun, which slightly changed the planet's shape and gravity. Yet, just like with the Pioneers, each conventional suspect struggled to fit all the facts or explain the precise magnitude of the speed boost. The flyby anomaly became a nagging piece of evidence that something, perhaps a subtlety of general relativity or an unmodeled geophysical effect, was still missing from our planetary playbook. It proved that cosmic mysteries are not confined to the distant void. They can be waiting for us in the intricate dance of a spacecraft swinging past its home planet, a silent hiccup in the gravity we thought we knew perfectly. This stubborn refusal of the anomaly to be fully pinned down for so long did more than frustrate scientists. It set imaginations alight. In the fertile space between a solid observation and a definitive answer, creativity thrives. While the thermal explanation gained dominance, a garden of more exotic, speculative theories bloomed on the fringe, each attempting to explain the Pioneer's drift with a grander cosmic brushstroke. One such idea looked not to the spacecraft but to the very fabric of the cosmos. We know the universe itself is expanding, with distant galaxies speeding away from us. Could this large-scale expansion have a tiny, local effect on objects within our own galaxy, like a gentle cosmic tide subtly slowing everything down? The math was intriguing, but most cosmologists found it a stretch. The expansion's effect on the scale of a solar system is thought to be utterly negligible, far too small to account for the anomaly. It was like suggesting the rising tide in an ocean could be measured by the slight dampness of a single grain of sand miles inland. Another theory dove into the strange realm of quantum physics. Even in what we call a perfect vacuum, space is not truly empty. It seethes with quantum fluctuations, a froth of virtual particles popping in and out of existence. Could the Pioneers, as they sailed through this quantum foam, be experiencing a novel form of friction or interaction with this underlying energy of space itself? This concept, while fascinating, remained highly speculative, lacking a clear mathematical framework to connect it to the precise, constant deceleration observed. Some even more creative proposals ventured into the territory of undiscovered particles or subtle, long-range forces that only manifest over astronomical distances. These ideas were not taken seriously by the mainstream, and for good reason. They lacked predictive power or testable evidence beyond explaining this one specific puzzle. Yet to dismiss them entirely is to miss their true value. These unconventional theories are not failures of science but a vital part of its process. They represent the boundless human capacity for wonder and hypothesis. When faced with a locked door, we try every key we can imagine, even the strange and ornate ones. This creative explosion is a testament to the Anomaly's power. It forced brilliant minds to look beyond the textbook, to question foundational assumptions, and to play with possibilities at the very edge of known physics. Each idea, no matter how fringe, served a purpose. It was a thought experiment, a stress test for our existing models. By entertaining them, even briefly, scientists clarified what the anomaly was not, and in doing so, they better defined the boundaries of what it could be. This is how science truly progresses, not by clinging dogmatically to old ideas, nor by leaping eagerly at every new one, but by creating a marketplace of hypotheses where every concept must eventually face the ruthless jury of data. The pioneer anomaly, in the end, was solved not by a revolutionary idea from the fringe, but by a deeper application of known principles. Yet the journey through that wilderness of speculation reminds us that the path to a final answer is paved with curiosity, creativity, and the courage to ask, even quietly, what if it's something else entirely? Every great scientific mystery has its detectives, individuals whose names become woven into the story itself. For the pioneer anomaly, two figures stand out, bookends to a puzzle that spanned their entire careers. The first was John Anderson, a soft-spoken but tenacious physicist at NASA, a jet propulsion laboratory. It was Anderson who, in the early 1980s, first noticed that faint, persistent drift in the tracking data. He was not looking for a revolution in physics. He was simply doing his job with meticulous care, comparing predicted trajectories against the actual radio signals. When the numbers refused to align, his curiosity was piqued. For years, he and a small team quietly analyzed the data, ruling out one mundane explanation after another. Anderson was the classic cautious scientist, methodical and patient. He resisted the initial rush to proclaim a discovery of new physics, understanding that extraordinary claims require extraordinary evidence. His life's work became this single, tiny discrepancy. He nurtured the mystery, presenting it at conferences, challenging colleagues to find the flaw in his analysis or propose a solution. He became the anomaly's guardian, ensuring it was not dismissed as mere noise. His dedication turned a navigational glitch into one of the most tantalizing puzzles in modern science. At the other end of the timeline was Slava Turyshev, a physicist whose drive was the engine of the final solution. Turyshev entered the story later as the thermal hypothesis was gaining ground but still lacked conclusive proof. He saw not just a physics problem but a historical one. The answer, he believed, was trapped in the decaying tapes and lost telemetry of the Pioneer missions. His decision to launch the Data Recovery Project was an act of sheer will. This was not glamorous work. It meant writing countless emails, making pleading phone calls, and physically traveling to dusty archives to hunt for boxes of 9-track tapes. He and his small team spent years becoming digital archaeologists, learning obsolete systems and file formats. One anecdote captures the effort perfectly. To read some of the oldest tapes, they needed a specific model of tape drive from the 1970s. They found one inoperable in a university warehouse. They then had to find another for parts and a retired engineer who remembered how to maintain them. For weeks, they carefully swapped circuit boards and cleaned magnetic heads, performing technological CPR on a machine older than some of the graduate students on the project. This was the unsexy reality of the search, a far cry from the dramatic image of a scientist at a chalkboard. Turyshev's personal drive was rooted in a profound respect for the data itself. He often spoke of the pioneers as silent witnesses, and he felt a responsibility to recover their full testimony before it was lost forever. His motivation was not fame, but closure, the satisfaction of balancing an equation that had hung open for decades. Between these two men stretched a vast collaborative network. This was never a solitary pursuit. It involved orbital dynamicists, thermal engineers, software programmers, and archivists. It required the constant operation of the Deep Space Network's giant antennas, staffed by technicians across the globe who kept listening long after the mission's official ends. The story of the Pioneer Anomaly is a testament to scientific persistence. It shows that breakthroughs are not always sudden eureka moments, but often the result of cumulative, painstaking effort over years. John Anderson planted the seed of the question. Slava Turyshev and his global team harvested the answer. Their shared trait was a stubborn refusal to let the question go unanswered, a belief that if the universe posed a riddle, humanity had the tools and the tenacity to solve it. This human dimension transforms the anomaly from an abstract physics problem into a relatable saga of curiosity, frustration, and ultimate triumph. It reminds us that behind every data point is a person asking why, and behind every solved mystery is a chain of hands passing the torch across generations. The key to understanding this solution lies in a simple but powerful visual. Picture the Pioneer spacecraft, a lonely silver and gold speck against the infinite black of deep space. It is coasting, its main antenna forever fixed on the distant blue dot of Earth. Now let us make the invisible visible. A soft crimson glow begins to emanate from the cylindrical radioisotope thermoelectric generators mounted on their long booms. This is waste heat, the byproduct of nuclear decay that powers the probe. The glow spreads, washing over the central electronics box and the struts, painting the craft in a warm internal light. But the heat does not stop at the surface. We see it as infrared radiation, streams of tiny particles called photons shooting away from every warm surface in all directions. At first glance, it looks like a symmetrical halo, a perfect sphere of energy, but look closer. The back of the large, dish-shaped antenna, pointed along the direction of travel, acts like a curved mirror. A significant portion of those crimson photons from the generators and the warm body strike this surface and bounce. Instead of radiating harmlessly out to the side or backward, they are reflected and focused, shot forward into the void like a faint, ethereal exhaust. The animation makes this imbalance starkly clear. The forward hemisphere of space now glows more brightly with escaping photons than the rear. This is the anisotropy, the lopsidedness that changes everything. Now we shift the view to see the consequence. Each of those forward-flying photons, though unimaginably tiny, carries a minute amount of momentum, and for every action there is an equal and opposite reaction. As the spacecraft throws these photons forward, it experiences a recoil. We visualize this as a continuous, gentle pressure pushing backward on the craft, like the softest possible thrust from a microscopic rocket engine pointed the wrong way. The animation superimposes a simple vector arrow growing slowly and steadily, representing this anomalous acceleration pulling the Pioneer back toward the Sun. Over days, this force is negligible. Over months, it becomes measurable. Over the decades of the mission, this relentless, self-inflicted photon push sums up to thousands of miles of drift, perfectly matching the mysterious data. The complex physics of thermal recoil is distilled into a silent, luminous ballet in the dark, showing how the spacecraft's own warm heart became the gentle break that baffled a generation. This lingering question of other spacecraft is a crucial test for any theory. If the anomaly was a universal new force, it should have left its fingerprint on every probe that ventured into deep space. Yet missions like Cassini, which spent years orbiting Saturn, and Ulysses, which soared over the Sun's poles, showed no clear sign of the same mysterious drag. Their silence is not a contradiction, but a clue written in their engineering. Unlike the spin-stabilized Pioneers, which coasted like silent, rotating tops, these later missions were far more active and complex. Cassini, for example, was three-axis stabilized. Think of it not as a spinning plate, but as a carefully balanced bird, using small thrusters and reaction wheels to hold a specific orientation without rotating. This constant minute activity to maintain attitude created a persistent, low-level noise in its trajectory data. A tiny, constant force like the Pioneer Anomaly would be utterly lost in that noise, like trying to hear a single raindrop during a thunderstorm. Furthermore, both Cassini and Ulysses executed many more planned thruster firings for course corrections and scientific observations. Each of these maneuvers imparts a small, uncertain change in velocity, making it impossible to isolate a steady, whisper-soft deceleration over decades. The Pioneer's greatest strength for detecting the anomaly was their profound simplicity. They were set and then they spun, sailing on with minimal interference. They were the perfect quiet laboratory. The very complexity that made Cassini a more capable scientific platform made it a terrible instrument for measuring a force this subtle. However, the precise tracking of these other missions served a different, powerful purpose. By analyzing their trajectories with incredible care, scientists could place an upper limit on any anomalous acceleration. They could essentially say, if a new force like the Pioneer Anomaly exists, it must be smaller than this amount, otherwise we would have seen it in Cassini's data. These constraints narrowed the window for new physics dramatically. The fact that no other mission showed an effect as large as the Pioneer's did not disprove the anomaly, but it strongly suggested the cause was not a universal law. It pointed squarely toward something unique to the Pioneer design or their specific circumstances. This cross-check from the rest of the robotic fleet was a silent vote of confidence for the conventional explanation. It helped corner the mystery, forcing investigators to focus on what made those two aging Pathfinders special, ultimately leading the search back to their spinning bodies and their warm, radiating hearts. That perfect blend of the ordinary and the extraordinary is precisely what gave this mystery its enduring grip. The Pioneer Anomaly was not just a physics problem, it was a narrative masterpiece. It possessed all the elements of a classic detective story that captivated scientists and the public alike. First, there was the clue, a clear and stubborn signal emerging from pristine data. It was not noise or a glitch, but a reproducible whisper that demanded an explanation. Then came the long timeline, a slow-burn investigation spanning generations, where early detectives like John Anderson passed the torch to teams like Slava Turashev's decades later. This was not a mystery solved in a week, but a saga that unfolded at the pace of the spacecraft's own journey, teaching us patience. Most compelling was the spectrum of suspects ranging from the utterly mundane, a simple heat leak, to the magnificently exotic like dark matter or rewritten laws of gravity. This range allowed everyone to engage, from the engineer who suspected a loose bolt to the dreamer who hoped for a cosmic revolution. It was a puzzle that invited speculation at every level, a riddle where the answer could be either a footnote in a manual or a headline in a textbook. At its heart, the story taps into a deep, romantic archetype, the lone explorer encountering the unknown. The Pioneer spacecraft were not just machines, they were our proxies, two silent envoys sailing into the absolute dark. When they reported back something unexpected, it felt like a message from the frontier itself. It triggered that primal human instinct of a scout returning from uncharted lands with a puzzling artifact. Is this a strange new rock, or is it a clue to a hidden world? The anomaly transformed cold telemetry into a cosmic signal, making everyone listening feel like part of the mission control team, hunched over the consoles, trying to decipher what the universe was telling us. This is why we are drawn to such mysteries. They fulfill a need for exploration and discovery that is baked into our species. We yearn for the maps to have edges, for the rules to have exceptions, because that is where true discovery lies. Ultimately, the Pioneer Anomaly stands as a quintessential space-age puzzle. It sits perfectly at the intersection of human ingenuity and cosmic law. On one side, it is a story of our own craftsmanship, of the wires, plutonium pellets, and parabolic dishes we cobbled together and flung into the void. On the other, it is a probe of fundamental physics, a test of whether our understanding of reality holds true in the silent vastness between stars. The tension between those two realms, the engineered and the elemental, is what gave the mystery its profound weight. The solution, when it finally crystallized, did not diminish that legacy. By revealing the answer to be a lesson in thermal engineering, it taught us something perhaps more valuable than a new particle. A lesson in humility, precision, and the incredible power of our own methods. It proved that the universe is knowable, not because it is simple, but because we are persistent. The allure remains because the story is not about a force that slowed a spacecraft, but about the human mind that refused to let the question go, chasing a whisper across the solar system until it was finally understood. The quest for precision did not end with the pioneers, it simply found a new frontier. The outer solar system remains the ultimate laboratory for testing gravity, a silent expanse where the faintest whispers of an anomaly can still be heard. To listen more closely than ever before, scientists are designing missions with one explicit goal: to measure acceleration with a surgeon's touch. Concepts exist for a dedicated deep space gravity probe, a spacecraft whose sole purpose would be to sail into the void with near-perfect silence and stability. Its design would eliminate the very thermal imbalances that haunted the pioneers, perhaps by using carefully balanced dual radioisotope thermoelectric generators that radiate heat symmetrically. Even more revolutionary would be its method of tracking. Instead of relying on the Doppler shift of radio waves, such a probe might use laser ranging. Imagine a beam of coherent light, a perfectly focused pinprick of photons, shot from Earth to an ultra-reflective mirror on the spacecraft and back. The precision in measuring the timing of that reflected beam could detect velocity, changes 100 times smaller than what the deep space network could achieve with radio signals. It would turn the spacecraft into a celestial metronome, ticking with atomic clock regularity across billions of miles. While such a dedicated mission remains on the drawing board, another active explorer is already providing a live test. New Horizons, having delivered its stunning portraits of Pluto, is now coasting into the Kuiper belt. Mission planners are applying every lesson learned from the Pioneer saga to its navigation. Its radioisotope thermoelectric generator is on a long boom. Its thermal profile is meticulously modeled, and its trajectory is tracked with obsessive care. As it journeys farther from the Sun, scientists will scrutinize its path for any hint of an unmodeled drift. The data from New Horizons is not just about the objects it flies past, it is also a continuous report on the fabric of space itself along its route. Each ping from the probe is a data point in the longest-running experiment in precision astrodynamics. This is the ongoing legacy of those two silent pathfinders. The Pioneer Anomaly set a gold standard for curiosity, teaching us that no force is too small to matter in the cosmic dark. It transformed deep space navigation from a practice of approximation into a discipline of exquisite measurement. Every future mission that sails past the orbit of Pluto will be following in the Pioneer's wake, carrying with them a simple, profound question inherited from that decades-long mystery: are we accounting for everything? The search for the answer is now a permanent part of the journey. So the grand cosmic whisper turned out to be a faint, self-inflicted sigh. The Pioneer Anomaly, a mystery that captivated us for decades, found its resolution not in the shadowy realms of dark matter, but in the warm glow of a spacecraft's own power source. It was a journey of scientific deduction in its purest form. It began with a tiny, stubborn discrepancy in the data, a whisper of a slowdown that refused to be ignored. That whisper launched a global investigation, a process of elimination that ruled out the spectacular one by one: no mysterious gas leaks, no unseen drag from cosmic dust, no gravitational grip from a hidden halo of dark matter. For years, the most elegant explanation was a subtle one: anisotropic thermal radiation, the idea that the pioneers were slowing themselves down by radiating their own waste heat in a lopsided way, like a faint photon rocket pointed the wrong way. Proving that hypothesis required a Herculean effort, a digital archaeology project to recover lost telemetry from obsolete tapes, feeding decades of temperature data into a supercomputer model of breathtaking complexity. The 2012 analysis was the culmination, a thermal portrait so precise it could account for the anomaly almost entirely. The universe had not broken its rules, we had simply, finally, learned to account for all of them. This step-by-step journey from observation to hypothesis to painstaking verification is often more valuable than any single eureka moment. It demonstrates the true engine of discovery, not a sudden leap into the unknown, but the slow, meticulous work of checking your work, of listening ever more closely to the data, and having the humility to follow it even when it leads away from the thrilling answer and toward the correct one. The pioneer's final gift was not a new law of physics, but a masterclass in the old ones, and in the persistent human curiosity required to understand them completely. The true legacy of the pioneer anomaly is not a revolution, but a profound refinement. It likely did not tear a hole in our physics textbooks, but it did force us to write a new chapter in our engineering manuals. The mystery taught a generation of scientists and engineers a humbling, essential lesson about the nature of deep space exploration. In the vast, frictionless void, there is no such thing as an insignificant force. Every watt of waste heat, every photon of reflected sunlight, every whisper of a radio signal carries momentum that must be meticulously tracked. The pioneers turned our gaze inward, compelling us to audit our own creations with an unprecedented level of scrutiny. We learned that to navigate the cosmos with precision, we must become accountants of the infinitesimal, balancing ledgers where the entries are measured in millimeters per second per century. This shift in thinking is their enduring gift, now embedded in the design of every probe that follows them into the dark. Today, those two pathfinders are silent. Pioneer 10 drifts roughly toward the red star Aldebaran, though it will not reach the vicinity for over 2 million years. Pioneer 11 sails in the general direction of the constellation Aquila. Their nuclear hearts are cold, their instruments still. They are now artifacts of human ambition, forever coasting on the momentum we gave them, carrying their golden plaques into the interstellar deep. Yet, their most important message was not etched on those plaques. It was written in their decades of unexpected drift, a masterclass in attention to detail that echoes in every mission control room. They remind us that in the grand theater of the cosmos, success often hinges on listening to the quietest voices, on understanding that in the vastness of space, even the smallest things matter immensely. What other whispers from the void are we only just beginning to hear? Share your thoughts on the great unsolved space mysteries in the comments below, and subscribe to join us as we continue our journey to the frontiers of science.